Thank you for the introduction. Indeed. So, yes, I'm going to talk about quantum computers as a tool. We've just heard a brilliant introduction from John about building scalable quantum computers, and so I'm going to talk about why this is so important and how we're going to use them as a tool, or how quantum computers will be used as a tool to help us get to net zero. And then the second part of my talk is around how we accelerate that. So how do we get to useful quantum computing sooner? So I want to start by talking more generally about computers and how we use computers today. So computers are used to design new products in many industries. I've picked just one example here in the aerospace industry. So right at the beginning of the 1900s, the Wright brothers discovered flight. And I think from this picture, I always get the sense that it was a real pain. Like they jumped off some ledges and really discovered what worked through trial and error. Today, we don't build airplanes like this anymore. We use millions of hours of simulations to design new wing shapes, new engines, and so on. So we use computers to simulate the underlying physics so that we can test thousands of ideas in the time it previously took to try one of them. And so as a result, aeroplanes work first time, right? The simulations are used to create a product that works straight away. And this has massively accelerated our ability to innovate in the aerospace industry. I think now if you compare that with other industries, so in the pharmaceutical space, you know, when we want to simulate the underlying physics, the proteins and atoms that interact to discover a new medicine, or if we want to simulate the way that electrons move across a battery, or the way that a catalyst reduces the energy consumption in an industrial process, this is where we hit a wall, right? This is where it becomes incredibly difficult. And the reason is not that we don't understand the physics. The reason is that the physics itself is complex. And so what's common across all of these three examples is that the underlying equations of motion are quantum mechanics. So the equations of motion that describe how a protein moves and interacts with a candidate medicine, how an electron moves across a battery material, or how a catalyst changes the potential energy surface in a process, in a chemical process. These are all explained and governed by quantum mechanics. And I think this is a really amazing equation, right? So we have Newtonian mechanics that describes the macroscopic world. So the way that a plane flies. You know, we use computational fluid dynamics. But quantum mechanics is what describes the microscopic world, the world of atoms. And my absolute favorite quote written at the time of this equation, so this has been around for many years, is by Paul Dirac. So in his paper, he says that, you know, with this equation, the underlying physical laws that describe mathematics, the theory of a lot of physics, and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations that are too complicated. And so what he's saying in 1929 is that we understand the equations of motion but we can't solve them. And that has remained true today. And of course, there are many people working on solving these equations. People approximate these equations. Computational chemistry, computational materials sciences is a huge and very successful field, but it is limited. We can also build larger and larger supercomputers. So we can use Moore's law to, or Moore's law has given us more and more computational power. But the problem is that these equations are essentially exponential. So even 10 years of Moore's law just gets us a slightly bigger system. And we never get to the point where we can really solve these equations of motion. And so this underlying challenge of solving quantum mechanics is a hugely profound and massively impactful challenge. It's something that will change the way that computation is used in multiple industries, and in particular those industries where at the core of the product design process is our molecular systems. About 40 years ago, Richard Feynman had this amazing idea that really the only way to solve quantum mechanics was to build a computer that operates according to the same laws as these equations. So to build a computer whose internal workings is the same as these equations of motion. Effectively, he was arguing that we should build a controllable quantum system if we're going to simulate quantum mechanics. That was a brilliant idea, and is now what we call quantum computing. So quantum computers are these controllable quantum systems, and they will be used to solve quantum mechanics. And so this will start an era of progress as significant as the invention of the computer. And so this will impact industries such as healthcare, where we can accelerate drug discovery or personalized medicine. It will accelerate improvements in manufacturing, so reducing the power consumption to produce many of the basic materials. And the development of new materials. So, for example, the production of fertilizer consumes a huge amount of energy worldwide. Or the transmission of power consumes about 4% of all carbon emissions. If we could develop high temperature superconductors, then we could reduce that 4% to perhaps something closer to 1%. So potential huge gain in getting to net zero. So I wanted to talk about how we make this happen in the rest of this talk. I mean, this is really the goal and why quantum computing is so important. So our mission at Riverlane is to make quantum computing useful far sooner. I had a great question just at the end of John's talk around the timeframes, right? And so this is a hugely important problem to solve, and we need to get there as soon as possible. So in order to unlock this huge potential, the basic problem is that we need quantum computers that are substantially bigger than the systems we have today. So the best quantum computers in the world can perform on the order of about 100 operations before failure. So they are the computers that John showed previously. They perform about 100 operations before the errors in the system start to accumulate to a point where what's coming out is just random noise. So we need to get from there to these applications, and these applications require hundreds of millions to billions of operations before failure. So we need a huge increase in the number of computations, and that's achieved by reducing errors at a system level. So there are a large number of qubits, and we reduce. We need to extract errors from the system, And that's achieved by something called quantum error correction. So quantum error correction is a process where we take the component qubits that have noise inherent in them and produce a computer that performs noise-free calculations, error-corrected calculations. So this is the basic challenge in quantum computing. It's a really huge challenge, and I don't think we should really play this down at all. I think it's actually a really wonderful challenge because if we can solve it, it has such a huge positive impact, and because, well, I just love these kind of really deep technical challenges, and this is really what we're doing here at Riverlane. So working on quantum error correction. So I want to talk a little bit more about what that involves. I appreciate it's not necessarily an area that people have come across before. So maybe I'll just give a quick introduction. So quantum error correction is the process by which we turn lots of noisy qubits into a smaller number of logical qubits, so error-free qubits. So just like classical error correction, we spread out the information in order to protect against any one error. So if an error occurs in one of the qubits, we're able to recover. Right. So this is the simplest error correcting code. Is that instead of sending a 0, you can send 3 zeros. So I send 0, 0, 0. Instead of sending a 1, I send you 1, 1, 1. Okay, and so let's suppose one of the bits is flipped. So you receive 0, 1, 0. So from there you can infer that I most likely meant to send you 0 because that only corresponded to a single bit, and had I sent you 1, there would have been 2 errors, so that's less likely. So you guess that I meant to send 0, and so that's a process of error correction, classical error correction, that can recover from a single error. So quantum error correction uses some of those same ideas. It has a lot more complexity. It's a really amazing theory, and it was something that was realized very early on in the development of quantum computing, that being able to error correct would be essential, right? Because this picture of a single qubit, it looks suspiciously like an analog computer. The state of this qubit is a ball. That analog computing is more powerful, sure, but it can't recover from errors. So there's an exponential cost in errors. So quantum computing is not analog computing, and the reason is quantum error correction. So we're able to correct errors in an efficient manner. So the implementation of quantum error correction is a big challenge in the field, and just to give you a sense of why, it's really because error correction is happening during the computation in a quantum computer. So between every operation that the quantum computer does, we run an error correction cycle, and this error correction cycle then determines things like the basic clock rate of the quantum computer. And there's a huge amount of processing that has to happen in that cycle. And so to give you a sense of scale, at the point where we're doing useful quantum computing, then we need to be processing on the order of 100 terabytes of data per second in real time, so during the computation. And so that's about the same as Netflix worldwide streaming, right? And as John was saying, that has to happen in a room, so in a very confined space. So this is a huge data processing problem. It involves the control system electronics and the ability to solve the decoding problem very quickly, and is a great combination of understanding how quantum computing, quantum error correction works, and how the classical control electronics functions. So we're not doing this alone, and it's a great privilege to be working with a huge number of really fantastic companies and academic partners on this. So at Riverlane, we work with some of the enterprise companies that are wanting to explore quantum computing right now because they are in industries that will be disrupted by quantum computing. We work with some of the companies that are building the underlying qubits and control systems, and with many of the leading academic labs. This is very much an industry that's coming from research into engineering. So the team at Riverlane, as I said, it combines quantum computing. So we have people like Earl Campbell, for example, who is one of the leaders in quantum error correction, working alongside people who have implemented error correction in other industries. So our head of silicon is Kozo Johar, who built some of ARM's real-time CPU systems that are used in, for example, the automotive sector. So this combination of skills is really essential to getting quantum computing to the point at which it's able to do useful computation and really have a positive impact on getting to net zero. I thought I'd just finish really with something of a call to arms. We are a global company and recruiting very quickly. So this is an area that you're interested in. If you're interested in the applications of quantum computing, if you're interested in the engineering challenges that go into making quantum computing useful, particularly around error correction, then get in touch. We are currently hiring at the minute. This is a big problem that will require partnerships. It will require lots of people from different backgrounds and different skill sets all working together.